Alright, so I'm going to go through some of these problems here. Uh, we'll focus on the ones you got wrong. So here this says a block of wood has been dropped from a tall building and has attained a velocity of negative 36.5 meters per second. How long has it been falling? So it just starts at the top and it falls down. It says it has an initial velocity, this would be in the y direction because it's falling down, of negative 36.5 meters per second. And it wants to know the time that it's been falling. So, if it's dropped, oh, sorry, this is not initial velocity, this is final velocity. If it's dropped, its initial velocity is 0 because it's dropped, right? It's not thrown down. And so then it says it's attained this at the bottom. So we've got our first kinematics equation. It says Vy equals V naught y plus AT. So Vy would be negative 36.5. That equals our initial plus negative 10 times time. So negative 36.5 equals negative 10t. We divide both sides by negative 10. And we get t equals 3.65 seconds. So that's it. Hopefully that made some sense. So it looks like you may have doubled it for some reason, and I'm not sure why. If you're thinking about a parabola, then maybe that's why you would have doubled it, but this is just falling straight down, no parabola, nothing, just straight vertical accelerated motion. Looks like you got 3, so number 4 here, it says a car traveling the legal speed limit with velocity negative v car with respect to the road. So if this is our road here, we have a car going negative, so this is negative v car, and it's approaching you in the opposite direction, and you are in this car going this way with the same speed but opposite direction, so you'd have positive v car. As the first car approaches you, what is its velocity relative to you? So both of these are assuming the road is stationary. Pretty good start. But then it asks you, it says, well, what is it from your perspective? Well, from your perspective, the road is coming towards you. So this chunk of the road is coming at you with your speed, v car, in the opposite direction. So if you're stationary, if your speed is 0, then that's how fast the road's going. Well, this thing's on top of the road, so it would have the road's velocity plus its original velocity. So it would have road's velocity plus its original velocity, which would be v car negative, and another negative v car. So this would be, its velocity should be negative 2 v car. Number 6, it says, an interesting setup here. It says, okay, we have north, south, east, and west. Right? And it says, okay, we got this first vector here from a plane traveling 525 kilometers per hour, 18 degrees east of north. So this is our north line, so this side would be east of north. So it's going to be going like this. So this angle here is 18 degrees east of the north line. And it says that we're going to draw that as lying along the x-axis. Well, normally we line our x-axis up with north, south, east, and west, but it's saying, well, for this one, we're going to put our x-axis right here. We're going to rotate our x-axis. So this is x and this is y, right? Okay, we did that. Then it says we're going to represent the velocity of another plane, traveling 478 at 75 degrees east of north. So it's still east of north, but this is 75 degrees. So this would come all the way over here. It'd be like this. So that would be our 75. So 75 is this big angle, right? So then it says, okay, if we put the first one on the x-axis, what would we say is this angle here, this representative angle? So we have this big 75-degree angle, we have a small 18-degree angle, and that's asking for this angle in between. So we just simply do 75 degrees minus 18 degrees to find the angle. We get 57 degrees. And the direction would be, well, we've got a lot of stuff going on here. So if we're looking at the x-axis here, this 57 degrees would be in this direction. So we would say clockwise from the positive x. Normally we want to go all the way around like this, but that would be a huge angle. We could still find it. But based on the answer choices given, we want 57 degrees clockwise. All right, and so remember, we'll rotate coordinate systems occasionally right now, but as we get into this next unit, this will make more sense why we can, or why we do rotate coordinate systems. Stone that's thrown horizontally from the top of the tower is traveling with its greatest velocity when it hits the ground below. So a stone is thrown horizontally, same instant a ball is dropped vertically. So one's going to go straight down, the other one's going to go hit the ground. Now, if they're dropped from the same height, they will land at the same time. It's because gravity will accelerate everything the same. But it asks which one is going the fastest. Well, this one starts from 0 and speeds up, based on acceleration of gravity. Okay, so it's going to speed up. We don't know what the final velocity is, but we know it's going to speed up a certain amount. Well, this one is going to be accelerated the same amount. So it's going to speed up by the same amount. So the increase in velocity, or a change in velocity for both of these, would be the same because it has the same acceleration. However, the one dropped starts from 0, whereas this one shot out to the side with the velocity. So whereas the changes in velocity are the same, since this one started with an initial velocity, we don't know what it is, but it says it's thrown up to the side, so it has to have something. So no matter what this is, if you add, this delta to 0, well, you just get the delta. And if you add the delta to, whatever this initial is, even if it's just 1, well, it's going to be bigger than delta. So the one that has the fastest velocity at the end is going to be the one that's thrown horizontally. So that's going to be our stone in this case. All right, got good. Here, number 9 says soccer player kicks a ball with a velocity of this and find the maximum height. Okay, so it goes up and it comes down. We want to find our maximum height. We know our velocity at this point is 0 in the y direction. So what we have to do here is we have to split our x from our y, from our initial. And so we can do sine for the y. So vy naught is sine, we would say the hypotenuse here times the sine of theta. So the hypotenuse in this case is our initial velocity of 14.4. Sine of 7 degrees. And the v naught x is going to be h cosine theta. So 14.4 is cosine of 7. So we'll get two numbers here, the x and the y. It's 14.4 times sine of 7, 14.4 times cosine of 7. So for the sine we get 1.75, and for cosine we get 14.29, and this will be meters per second. Okay, 14.4. So now, it wants us to find this max height here. What is this? Okay, well, if we launch the ball from 0, our initial position would be 0, and we're looking for final. Okay, so we've got velocities, and we've got the y's, or displacements, and we're looking for the height, which is displacement. So the only thing we don't really have here is time, so I don't really want to use the second equation. So the only equation, kinematic equation, that doesn't have time is our third one. So it'd be Vy squared equals V naught Y squared plus 2A Y minus Y naught. So Vy is our final velocity, so at the top point that would be 0. V naught Y would be our initial here, this 1.75 squared plus 2 times negative 10. And then we do Y minus Y naught, which is 0. So we multiply this together, get negative 20, and then distribute that to each. Well, it's going to be 0 here. So what is 1.75 squared? 3.06 minus 20y. We can add 20y to both sides. I have to move over here. Don't want to flip over for this, so we get 20y is 3.06. So we divide both sides by 20. Y would equal 0.153. So in this case, the vertical velocity would only be like 15 centimeters, so not very much there. All right, so I'm going to do question 10 here, and then you can think about the others on your own, but it's important to note that these problems go from easy to hard, and so you're missing a lot of these initial ones, so the harder ones don't really matter until you can get these initial ones down solid. So number 10 says, okay, you have a ball is thrown with a velocity up, an angle of 22.7, and an angle of 63 degrees. Okay, what's the vertical component of the velocity? So we have Vx and Vy. So it just wants the vertical component, so all we have to do is find this. So that would be 22.7 times the sine of 63 degrees. So I don't even need to find x, because this is all it's asking us to find. 22.7 times the sine of 63 degrees gives us 20.23 meters per second. So that's it. I guess we can do 11 since that one didn't take very long. In a diagram, the length of the arrow represents the magnitude. So remember, I'm drawing all these arrows because vectors have magnitude, that's the size, and the direction. So the direction of the arrows obviously that indicates the angle. You know, this is the angle here. But the magnitude represents the size. So this is a certain size vector. This one has the same direction, but it's smaller, and this one has the same direction, but it's bigger. So the magnitude is represented by the length of the vector, and the direction is represented by the angle, or the direction it's pointing. Okay, hopefully that's helpful. Once you've practiced some of this stuff, then we can discuss the rest of these problems. But if you don't know what the word magnitude means, or that the size is this, hopefully you can see how like doing things like this or more complicated stuff is going to be a lot more difficult. So we've got to focus on the basics here.